Here is an ethane molecule, one of the very simple organic compound. For an ethane molecule, there are two carbons connected by a sigma bond. We know that for head-on sigma bond, you could rotate along the carbon-carbon bond freely. However, based on the relative three-dimensional arrangement of the atoms, not every conformation is of the same energy. What we're going to do today is I'm going to show you how to describe a conformation utilizing a three-dimensional conformation utilizing a two-dimensional Newman projection. For instance, when you are trying to describe this particular conformation, what you could do is you could view from this carbon directly down the line, look at this carbon. Okay, under that circumstances, you could describe the three-dimensional structure on the board in two-dimensional way. To do that, you describe the first carbon, the carbon in the front, as a dot. Okay, and then you describe the rest of the hydrogens utilizing a Y-shaped bond. I'm going to use one of the green to help us track the bond rotation here. Okay, and you could describe the carbon behind utilizing a circle. Okay, didn't do a perfect circle. All right, so the three substituents bonded to this carbon could be described as a upside down Y. Again, I'm using a green bond to help us to understand the bond rotation a little better later. Okay, so this particular conformation is called a staggered. All the hydrogens are positioned furthest away from each other, and under that circumstances we could describe the three-dimensional relationship between these two green hydrogens, and they are not directly bonded to each other. However, we could look at the three-dimensional from this hydrogen to this carbon to this carbon and this hydrogen. If you look along the carbon-carbon bond, they have a 60-degree dihedral angle, okay, or called torsional angle. We could also rotate the carbon-carbon bond, okay, to 60 degree. And by doing that, you come up with an eclipsed conformation. Okay, all the bonds are opposed to each other. We could also describe an eclipsed conformation by again drawing the carbon in the front as a dot, okay, and write your Y-shaped substituents on the carbon. We could also describe the carbon behind as a circle, okay? Because they are opposed to each other, it's really difficult to really draw out the rest of the hydrogen. What we do is, whoops, this should be an H, not a Y. I've been talking too much Y's, obviously, right? So in order to do that, usually you just try to draw a little line right next to the bond for the front carbon to make them as close to each other as possible. Usually that's how we describe eclipsed conformation. Under that circumstances, if you look along these two green hydrogens, their dihedral angles are 120. And if you look at the two hydrogens that are eclipsed to each other, okay, for any of them, and the dihedral angle is 0 degree, okay? And so you could actually draw an eclipsed conformation when the two green hydrogens have a 0 dihedral angle, okay? And you could also continue drawing along the line by rotating the carbon-carbon bond. Keep in mind when you are rotating a carbon-carbon bond, keep the relative three-dimensional position of the front carbon constant, only rotate the back, you get the dihedral angle of 180, dihedral angle of the two hydrogens 240, 300, and back to 360 or 0 degree. Okay? And this particular form, as I mentioned, is eclipsed. Okay? And for the eclipsed conformation, there's actually repulsions among the hydrogens, and under that circumstances, this conformation is of higher energy. And therefore, we actually could describe the potential energy of different conformation associated to the corresponding dihedral angle. Okay, we can start with 12.6 kilojoule per mole. That's for any of the eclipsed form. And once you rotate the carbon-carbon bond, the potential energy drop to 0 for a staggered conformation, and going up to 12.6 for 120 degree dihedral angle, move down to 0 for another staggered conformation when the dihedral angle is 180, and move up to 12.6 again for 240, and move down to 0 for 300, and keep moving. Okay, this is how we describe the different Newman projection along with the different dihedral angle to describe or to understand the potential energy associated to different conformation.